So everyone, welcome to the channel. In this video, we are going to do an analysis of the beam. In fact, this is a simply supported beam, but the member here D is overhanging uh, by 3 meter from the support D. We will be constructing a shear force and the bending moment diagram for this beam. So let's start here. Let me just move this aside. Okay. So here at A we have a hinge support and at D we have a roller support. Let us first try to write the reactions for the hinge support here. Okay, so let me make the pin over here. As you can see here, there will be two reactions in this hinge support, a vertical reaction, and there will be this here a horizontal reaction also. But in fact, in this beam, there is not any horizontal load acting, so this reaction here will be zero. So no need for the horizontal reactions. So I am going to write here only one vertical reaction at A, that I am going to write at RA, and at D point, this is a roller support, and in case of roller support, there will only be one vertical reaction, and I am writing here RT. Okay. So before proceeding any further, we have to note here is that at this point at this point B, there is a load of 20 kilonewton which is acting at a distance of 0.5 meter, but it is acting at offset from B. So it is not acting directly at B but at 0.5 meter from B. So for that, we have to first change that couple into equivalent. Okay, change that load into equivalent couple. So let's see what can be done here. So in such case, first at point B, okay, first at point B, there will be a couple acting due to this 20 kilonewton vertical force. So now let's first find the moment at point B due to this 20 kilonewton load. So it will be 20 into 0.5, that is 10 kilonewton meter movement or couple, but that will be acting in a clockwise direction. So similarly, there will be one vertical force, purely vertical, that will be acting at point P, which will be equals to the 20 kilonewton, same as that given here. So what we have done here is that at this point B, there is one load of 20 kilonewton, which is acting 0.5 meter from this point B. So due to this load at point B, first, what you have to do is just apply this 20 kilonewton directly at point B. Okay, so first 20 kilonewton is directly applied at point B. Then, since this 20 kilonewton is acting at some distance from B, at some 0.5 meter from B, so you have to calculate the moment which this 20 kilonewton force will produce at point B, and that will be obviously a clockwise movement, and the value will be equals to 20 into 0.5, so it will be 10. So like this we have done the equivalent load here. So now I didn't have to see this. Now there is no need for this. I can just deduct this load because I have already converted this 20 kilonewton into a point load 20 kilonewton and a clockwise movement of 10 kilonewton meter. Okay, so now to proceed further and to find the RA and RD, I have to first find the equivalent point load which this UVL will be giving producing. Okay, so the equivalent point load, as we know, in case of UVL, in case of this type of UVL loading, if it is maybe here it is 5, so equivalent point load will be equals to the area of this UDL if the base is, as you can see here, the UVL is acting from point C all the way to the point E. So our base is 6 meter. So the equivalent point load will be 1 by 2 into base into height, that is area of this triangle, and it will come out 15 kilonewton. Now you have to bear in mind that this equivalent point load, which is 15 kilonewton, now we act at a distance of this distance. Okay, so this distance will be 2 base by 3, so that is 2 into 6 by 3, and that will come out as 4 meter. So let's draw that over here my equivalent point load, which will be equals to 15 kilonewton. We have already calculated here 1 by 2 into 6 into 5, and this is acting. Okay, so this is acting from point C all the way to a distance of 4 meter. Okay, in fact it is acting 1 meter right to this point D. So I hope it is clear up to here. Okay, so now to calculate the support reactions, at first I am going to take the moment of all these forces about the point A, and I am taking the moment in clockwise direction as positive, uh, equals to 0. So for A, okay, so let's see what I will get. Okay, so let's find the moment. Okay, so what force will keep moment? Okay, you can see here at point B there is 20 kilonewton force. This 20 kilonewton force will produce a moment of 20 into 20 into 2 in clockwise direction, so it is positive. And there is 10 kilonewton meter couple which is now acting at B. This couple is acting clockwise at B, so we have to directly add here 20. But keep in mind we should not multiply by any distance because it is itself a couple, and so there is no need for that. Now coming to the 15 kilonewton, which is here, this is the point load 15 due to the equivalent point load of UVL. So it is also giving clockwise movement. You just have to do it plus 15 into distance of this 15 load, this 15 load from point A, which is 2 meter plus 2 meter plus 4 meter. So that will be 2 plus 2 plus 4. Okay, now this RD support reaction will also produce a movement at A, but that movement due to this RD will be anti-clockwise. So minus RD into distance will be 3 meter plus 2, and that will be 7 equals to 0. If you go on solving, you will find the RD. RD will come out as, I think it has to come out as 24.28 kilonewton. Okay, so let me first check it rapidly. Okay, so my RT has come out as 24.28 kilonewton. Now to find RA, you need to find the RA. So there is an easy way. You can either now do the movement at point D. Okay, you can do the movement, take the movement about the point at D. Okay, so let's do it. Okay, or if you want to take the moment at D, so let's go from the start. Look at this array. Array will also produce a moment at D point, and that will be acting in clockwise direction. So you have to write RA into distance will be from A to D. The distance is 3 plus 2, 5 plus 2, 7. So let's write here 7. And this 20 kilonewton now. This 20 kilonewton will produce anti-clockwise. So minus 20 into distance will be 5. Similarly, that 10 kilonewton meter couple, which is at point B, this is clockwise. So just add here 10. Now the next part is due to this 15 kilonewton point load, and this 15 kilonewton is in fact lying at, look at this distance, 1 meter from point D. So it will give clockwise movement 15 into 1 plus 15 into 1 equals to 0. So if you solve this RA, you should get as 10.72 kilonewton. Okay, so we have found the two reactions, one reactions at RD and the other support reaction RA. If you want to check either if you have done it right or wrong, you can just take the particle for summation. uh, Summation Fy, upward is taken as positive here. So for the beam to be in static equilibrium, all the vertical forces acting here shall be 0. So let's do this. Ra minus 20, you don't have to write the couple here because this is not a vertical force, minus 15 plus Rd, it has to come to 0. So if you substitute 24.28 minus 20 minus 15 plus 10.72 equals to 0, yes, this part will be 0. So what we have done is true, and our reactions is correct up to now. Okay. So we have got the reactions here, Ra at 10.72 and Rd at 24.28 kilonewton. Now what we have to do is, now we have to proceed further for the shear force calculation. Okay, so we are going further with shear force calculation. So let me increase the thickness of this. I think this will be fine. Okay, let's see here, right? So since at BA, okay, shear force, first we have to know the sign convention. Shear sign convention for shear force will always be like this. Okay, left up, right down. This is the sign convention. You can imagine a section at the between. Okay, let's see how is that. So at a point at BA, that is shear force is represented by symbol B. At a point, our shear force is 10.72 kilonewton, and that is taken as positive. Why? Because A is the leftmost corner or the leftmost point of our beam. So for the left, you have to see this sign convention. Up arrow is taken as positive, and here 10.72 is acting upward. So it is taken as positive because this arrow matches with this arrow. So BA is 10.72 and it is obviously positive. Now look at this point B. Okay, so you are doing shear force calculation. So for now, I don't have to see for this 10 kilonewton meter movement. It doesn't make sense now. You just have to look at this 20 kilonewton force. Now, since at point B a 20 kilonewton vertical force is acting, so you have to do this in two way. You have to see VV left part. Okay, so VV left is nothing. You just imagine that you are somewhere just to the left of over here. Okay, so now I am standing over here, I am looking for this point here, and still I have to look towards the left of it. So okay, so I am now situation here at this point, and I am looking towards the left. So what do I see? I see only this 10.73 kilonewton, and that is also acting upward, which matches with this arrow. So this is also positive 10.72. In fact, it is same as BA. Now let's jump to the just right of B. Now I have arrived at this point. Okay, this point. Now again I have to look towards, always you should look towards the left. You can look towards the right also, but for now I am looking towards the left part of the beam. So now I am here, that is BB left. This is over here. Okay, I have reached just to the right of B, and I am looking towards the left. What do I see? I see one force, that is 20 kilonewton, which is acting downward. 20 kilonewton is acting downward, and I am looking towards the left. So for the left, we have to see this arrow, okay. The arrow says upward will be positive, but this 20 is acting downward, so I have to write this 20 as negative, minus 20, and I can see 10.72 also, that will be positive, plus 10.72, and it will come out as 9.28 kilo Newton, but this will be negative. Okay, so I am getting the shear force at the right part of the point B as negative. Now let's move on to the C point. Okay, so for the C point, let's see here, shear force at C. I'm just at C. How much will be at C? So I'm at this point here, and I will look towards the left again. What do I see? I will again see this 20 kilonewton and this 10.72. There is no any other forces. Please keep in mind, you don't have to see for this 10 kilonewton meter, because this is not a force, actually this is a couple. Okay, so for shear force calculation, don't you dare to go for the couple, just only see the transverse forces. So again I can see 10.72 kilonewton and 20, so this will again come exactly like the above one. So this is just like 9.28 kilonewton. Okay, now let me go towards the D point. Okay, so I think now there will be some going to be some issues here. Okay, I am going for B D. Now I have to do left and right because at D point there is one reaction 24.28. This force is acting at point D. So whenever there is some transverse force acting at a particular point, so my point of interest is now point D. So this force is acting here at point D. So always you have to see just immediately to the left of D. This point will be VD, left, immediately to the left of D, and this point is as VD, right, immediately to the right of this. Always you have to do like this. Whenever there is a transverse force acting at a point of your interest, you always should check for immediate left and immediate right point. So let's do this PD left, and let's see here, right? So if you so it means that I am now over here just a little bit to the left of D, and I will be looking towards the left of this beam. So what do I see? Okay, so first thing that I will see is this triangle. Okay, let me change the color this to the green one. So if I am over here, I am just to the left of the a little bit over here, I will see this UVL part. Okay, this triangular part. Okay, so for this triangular part, I first need to find the equivalent point load. If this is going to be the equivalent point load of this triangular part, uh, so what will be this value? 1 by 2, the base of this triangle, this is 3 meter from C to the D. I am only looking for C to D. This is 3 meter, and the height. Let me write h. Okay, 1 by 2 into 3 into h. Now first I need to first calculate the value of this h, which I don't know till now. So let me do that over here to the corner in triangle. Let's see in triangle CDE. Okay, in triangle CDE, what we can find is that this triangle, this big triangle from C to E, and this small triangle which is right now hatched in only green part, these two segments of the triangle, they are similar triangles. So what I can write is that h upon 5 must be equals to 3 by whole base is 6. So h will came out as 2.5. Okay, this 3, this is like this, so h will come as 2.5. So what will be my this equivalent point load? 1 by 2 into 3 into h. Now h is how much? 2.5. So 1 by 2 into 3 into 2.5. If you go on calculating like this, you will get it as, okay, let me do it here. So this will come out as 3.75. Okay, this value is 3.75 here. So let me write it down. This calculated by this part is coming out to be 3.75 kilonewton. Fine. Now again let's switch this to, okay. Okay, so left, what I will see, the first I will see this 3.75, this is acting downward, but the arrows will go upward, so this is negative minus 3.75, and again minus 20 plus 10.72. So I don't know how much this will come. Let me just calculate this. 3.75. Okay, okay, so this will come as negative 13.03 kilonewton. Fine, so towards the left of the point D, negative of minus 13.03 kilonewton is coming. Okay, so there's no issue right now. So let's go towards the right of this point D. Okay, so now I am wanting to see over here. Okay, I have reached out now this point to the right over here, right of the D. If that is not clear over there, let's make a small figure over here. So this is point D. Now I am in this figure, so if I have to change the color, so I am over here, this is VD, just right, and again I have to look to the left of the beam. Okay, to this left part. So what do I see is that now I have already crossed this point D because I am at the right of this section. Now there is one additional force which I will see, and that is 24.28 kilonewton. This additional force I can see. So the value is same as this value. Okay, so what I have got in this value, vd left plus additional, what I will see, I will see this 24.28 kilonewton, which is acting in upward, so it is positive. So this shall come out as 11.25 kilonewton. So I hope you understand this part. And now for the e portion. Okay, now for the ve, what I will get is, now let's see here what's about the VE. Okay, so how much shear force will be at this point, how much shear force will now be acting in this point. Just imagine you are over here at E point and you are looking towards the left. What you can see, this has to come out at 0. This will always be 0 for this part, but to check you can just do it for, you have to see all of the section towards this left, and it will obviously always come out as 0. Okay, so, if you want to check you can just do it as, what we have to do it like 10.72 positive minus 20 minus 15. Okay, plus 24.28, we already did that, it came out as 0. So last point it will always be 0. Okay, so before proceeding further to the bending moment diagram, let's first make the bend shear force diagram. Let's first plot these values in a graph, or try to make a plot of these values, and then we'll proceed with the bending moment diagram. Okay, so I want to plot the shear force diagram in this corner. Let me first, okay, so now I'm ready to plot the shear force time. Let me try to first make a very straight line. I think it's very difficult, going to be difficult for me in this digital board. Okay, now I'm just trying to do it. Okay, I think it's fine for now. This is my point A. I didn't need to show the supports here in the diagram. This is now my point B, my point here at C, my point at D, and this is my final point E. Okay, okay, let's do a little bit change here. Okay, it's fine for now. So a is 0. Okay, so let me tell you the basics. I will be plotting, this is point E, let me name it later on. So for the positive points I will be plotting is upward, and for the negative, now I will be plotting it downward. Now for this point at A, so okay, here is my A, there is the shear force value. Let's look at A. The value of shear force is 10.72 kilonewton. It is positive. Now let's plot this 10.72 upward. Okay, so this will be like this, 10.72. Okay, let's draw a vertical line here at point A. That's fine. Now this is point B. Okay, this is point B, and at point B left we got the same value, 10.72. Now if this is our my point B, so up to the left, that is 10.72. For this left, first draw left, same value, means a straight segment up to here. The value is 10.72 for the left. Okay, I am not plotting for the right now, this is just for the left portion. So make a horizontal line here. This is 10.72 for the left part. Now for the right, the answer is negative of 9.28. So for the negative part, let's draw it downward. Okay, negative is over here and the value is 9.28. So what we have to do, this is left part, this is right part, so join left to right. Okay, okay, so this is it, this is positive, now this is coming negative. Now we are at point C, this is our point C. At point C the value is same, you just have to make a straight line all the way to here, because this is also same value at as of B right. Okay, so at point D left, this is now my point D. If this is my point here at D, D left value is negative of 13, and this is negative 9. 9 means it's little bit larger than 9, so this is 13.03. Okay, I think this is fine. Okay, and D right, it is 11.25. Let's make me first this 11.25, a little bit further off from 10.72, so I think this will be justifiable. 2 5. Now look at here. First I have to join this point to this point. Okay, so I think you all will be guessing right now that I should draw a line like this, a straight line like this, but that will be very mistake, because look at here, from C to D you can see here, from C to D there is a UVL, that is a triangular load. Okay, in case of triangular load, your shear force diagram will never be a straight line. In fact, it has to be a curved line. Okay, so for the curve, I will be joining here like this. So the correct graph will be, that will be drawn by this green line, and it has to be like this. Okay, so this value will go on like this one, the green graph. Now, okay, so let me find my eraser. I can find the eraser. Okay, I find this eraser, I got it. So I have to rough this line. This is actually not a has to be parabola. Okay, so this line is now, this line is parabolic, square parabola. Okay, this will always be a square parabola. In case, in which case, okay, in which case it will be square parabola, it will be in case of UVL for the shear force diagram. In case of uniformly varying load or triangular load, this graph will be, this curve has to be plotted as square parabola. I will, maybe I will show in the next of the videos, because it will take a little bit long, it will be lengthy if I show you how it coming at square parabola. For that we have to cut a section in between C and D, and you have to find the equation of that section, and it will be in the function of x square. So that's how it's coming as square parabola. Okay, fine for now. So let's draw this straight line from this left to all the way to this 11.25. Okay, okay, this is it. Now at E point, this is coming at 0. Just you have to join this point with this point. Again, the rule is there won't be straight line. So you never do like this. Okay, this is wrong in exam. So what we have to do is again make a parabola. So I am going with this one. Now this part positive, this whole part is negative. You can, you can draw a proper hatch. So my shear force diagram, this is my shear force diagram. I haven't shown the units here, you can write it here as Newton. Fine, so this is my shear force variation for the, okay, so now let me change the color to the black, and what I want to do it now is calculation of bending moments. Okay, calculate, represented by m. The sign convention, you always remember, sign convention is like this. Okay, for the both, this is left part, this is right part. So for the left also it is going upward, and from right also it is going upward. So this is showing that bending moment will be positive when here this beam is bending or showing this type of bending. Actually this is a sagging shape. So whenever the shape is sagging, this is sagging, sagging bending is considered positive. So here comes this sign convention. Okay, so remember that. Now let's do it. Okay, ma, automatically movement at point A has to be 0, because A is what type of support? This is roll, sorry, hinge support. So in hinge movement will be 0, it allows the rotation, so movement at A is 0. Now let's come to point B. Now look here, again we have to do at B point C, there is no uh, at B point, there is one couple of 10 kilonewton meter is acting. Now for the bending moment calculation, you have to take consider of this 10 kilonewton meter couple. Okay, so whenever in finding the bending moments, whenever a couple is acting at a point, you always have to do the left and right, as we have done previous in the shear force calculation. So what I mean is that you have to see for NB just left. That is, I am at this point. Okay, this point I'm looking towards the left. let's see if I am at this point and looking towards the left, which forces, how many forces will produce the movement at this point. Only one force, because there is only one force towards the left of this point, that is 10.72 kilonewton, and it will produce a bending moment of 10.72 times 2 meter. Now actually I am a little bit from the left of this support, but that this much distance, it doesn't means anything because it's very short. I am only just towards the left, that is limit extends to very small. So just ignore that distance and just to 10.72 into 2. It is positive because look at this arrow, the arrow is going upward, this sign is also going upward, this arrow, so this is positive, or in a sense from the left, so clockwise movement has to be taken positive, and this 10.72 is giving me clockwise at this point. So the value itself come as 21.44 kNm, that is kilonewton meter, and it is positive. Very good. Now towards this right, okay, and be right, that is now I am here at this point. Okay, I'm sorry for this. I am now at this point and wanting to look towards the left. So how many forces will give me movement? One the same, this 10.72 kilonewton force will produce a movement at this point. Okay, which point? At this point, and it is same as above. Now you don't have to increase this 2 by any other distance because I am only just to the right of B. I am not further away. I am not that much far from B. I am only a little bit away from B. So you don't have to consider for this distance. Just write it here as 2, 10.72 into 2. Now next part I can okay, next part is this 20 kilonewton force. Now look at here. This is my point P. I am just to the right of P over here. And at B there is one vertical force 20 kilonewton is acting. Do you think this 20 kilonewton force will produce any movement at this point? Look, I am here at this point. Do you think any 20 kilonewton will produce any force at any movement at here? No, because this distance is very small. This is like 0.0001, and if you do 20 into 0.0001, that is approximately equals to 0. Okay, so no need to do that, you don't have to do. But the other thing is that, other thing, look at here, this is 10 kilonewton meter couple over here, 10 kilonewton couple. You can see the 10 kilonewton meter couple acting at B if you are at this point. So you have to take into consider this 10 kilonewton meter, but don't take into consider of this 20 kilonewton force. Okay, because 20 kilonewton force multiplied by a very small distance will come close to 0. That is very insignificant or irrelevant in this calculation. But this 20 kilonewton force is a moment which is applied at this point. So if you are even a few millimeters away from B and you are looking towards this left, you will see this couple. So you have to take into consideration of this couple, and this will be positive. Okay, so plus 10, because this couple direction and this left part arrow matches, both are clockwise, so it is taken as positive. So the value, I think it has to come out as positive 31.44 kilonewton meter. You can check of your own. Okay, that's fine. Now let's move on to C point, the bending at C point. That is, I am now at C point and I want to look towards the left. Now see how many force will give me moment. Let first start with 10.72. This will give a moment of 10.72 into total distance will be 2 plus 2 4. Okay, so how come this 4? 2 plus 2, 10.72 is 2 plus 2, 4 meters away from C, plus, sorry, plus, okay, 10 kilonewton meter couple, which also give, it will also contribute to the movement. And just write 10, you don't have to multiply by any number because it is already a couple. Okay, just 10. Now see here, the trick is this 20 kilonewton, this force is also producing some movement at C point. Okay, so how much this will produce? 20 into the distance will be 2 meter, but this 20 kilonewton will produce a movement of anti-clockwise. We just have to do it as 20 into 2 but negative. I think it has to come around as 12.88 kilonewton meter. Okay, let me. Okay, now so I have to proceed further. We have done it to till the point C. Now let's move on to the point D. Okay, so I would be writing over here. So we have done it till the point C. In C it came out as 12.88. We'll plot it later. So let's move to the point D. Now again, what in point D, what is happening? In point D, there is one load 24.28 kilonewton, but there is no any couple acting at point D, so you don't need to do left and right. In case of bending moment, unless and until there is any couple or a moment acting at that point, you don't have to do left and right. Only in shear force, if there is vertical force acting, you should do left and right. But in case of bending moment diagram, in case of bending moment diagram, but in case of shear force diagram, only you have to do in bending. Unless and until there is a couple, you should not do anything. Okay. So now just proceed further for the movement at point D. Okay, so I am going to find this movement at point D, and again I am looking towards the left of the beam. That is, you can imagine you are at this point here. I think I have to do this in another color. Let me choose this indigo. Okay, so I am at this point. This is D point, and I shall look towards the left. So looking towards the left, what do I see? First I come across this thing, this point load. We have already done how it came here. So let's find the distance from this point load to point D. This distance will be b by 3. Okay, yes, good, 3 by 3. So this is 1 meter. If you don't know, you should go and check for the CG of the triangular section. This will always coming at 3 by 3, that is 1 meter. This part will be 1 meter. So let's find the movement due to this. It will definitely give me negative bending moment. You can check for the sign convention. Clockwise is positive, but this is giving me anti-clockwise. So what we have to do is just write minus 3.75. The distance will be 1. Okay, now this 10 kilonewton clockwise, add here 10. This 20 is again anti-clockwise, just minus 20 into distance up to the D is 5 meter. This 10.72, it will give me a positive as per the sign convention. 10.72 into total distance will be 7. Okay, now let me calculate how much it will come. I think it's okay, I just calculated. It is coming around 18.75, but I think that is in negative. 18.75, you should do it yourself. Okay, 18.75 kilonewton meter, but that is negative. Now move towards the E point. E point is always 0 because what is E? E is the free end. Okay, free end of the beam. There is no support. There is no support at E. So whenever there is no support or free end of the beam, the bending moment at that point will always, in every case, in any load, it always has to be 0. Okay, that's good. Okay, so there is one interesting feature here. Let's see. Okay, okay, this is the most important, interesting, or you can also say the salient fix feature or the important feature of this beam. Now look at here. If I go on plotting this diagram, I'll show you a little bit later on. Okay, okay. For now, let me make the diagram. Then I also write this interesting feature. Let me first plot the diagram. Okay, I think that will be a best approach to show you. Yeah. Okay, I have done that here first. The diagram is over there at the corner. Let me first try to make a straight line. Okay, over here. I think this much is good. Let me first make a straight line here. Okay, let it be a very straight line. This is point E, this is my point A. I am trying to draw a bending moment. Let me see how much successful I will be. So what I know is at A point it is 0, so I have plotted this is 0. Now if this is my B point, what you can see at B left it is positive. Again I am plotting positive upward and negative downward. Most of the writer will do the exact opposite. It's fine, you can take wherever positive you like. Okay, this is just a matter of sign convention or a plotting norm. So At B left, that is positive. So let me draw here positive 21.44. This is my 21.44. Okay, this is a bit early, I think. Let me drop this. Okay. Okay, this value is 21.44. So what I have to do, this is B left. Okay, this is B left. From A to B, is there any load in between? No. So just draw a straight line like this. No curve. Okay, whenever there is any triangular or rectangular loading, only then there will be curve. But in case of no loading from A to B, there is no load in between the beam. Just start it with the this straight line. This is positive. Now I have done up to here. So at the right part, this is 31.44. So just increase a little bit here. Same, this is also positive. So on the same side, this is 31.44. Okay, so from here, okay, so you can just, okay, drop this part also. You don't have to show this line here. You can show, but it's okay if you don't show also. So the diagram is like this. It went from 0 from here to 21.44 at this point, and then it rised, it peaked to this point 31.44. Why? There is a gap of 10. Do you think that why there is a gap of 10? Because there is a 10 kilonewton couple acting at P. So whenever a couple is acting, there will be certain torque in the bending moment diagram, and then torque is over here. Similarly, you could have seen that torque in shear force diagram over here. The torque, this torque will be Alpine equals to 20 kilonewton. Okay, so in shear force, the torque will be felt if there is an point load. In case of bending moment, the torque will be felt in case of couple. Okay, so this is it. We have done it till now. So let's move on to point C. Okay, in C point, my bending moment has came out to be 12.88. It's still positive. 12.88 is very low value. So I think the scale, actually I make it a little bit larger. Let's make my value 12.88 over here. I don't think this is suitable, but let's do it. So in between B and C, again there is no load on the beam. So let's draw it straightly like this. Okay, this is again straight from B to C. This is stress. This value is 12.88. Okay, let's not go into the scales or dimensity of this plot. Okay, now let's go to this point. Actually, I'm going to make it D point here. Now what I can see is in D point there is negative bending moment diagram, so I have to plot it downwards. Okay, this is downward at point D. Okay, this is my point. Okay, point D point, downward it is 18.75. 18.75. Okay, so I have to join this C point to this D point. Okay, let's leave it for now. Let's leave it. Let's see the E point. It is 0. In between D and E, what type of load you can see? In between D and E, there is a triangular load. So in such case, there will never be a straight line. There will be a curve, and that curve will be like this. Okay, the name of this curve. Now look, this is not a square. This has to be a cubic parabola. Okay, in shear force it was square parabola. In bending moment there will be 1 degree higher curve, so it is cubic parabola. This one is negative here. Law. Now let's come to the C and D point. This is my D point. Okay, this is my, okay, this is my D point. Okay, okay, this is my D point, and this is my C point. I have to join this 12.88, which is coming as positive here, all the way to this negative. So which graph do we think it is suitable? By which curve I have to join this? So looking at this here first diagram, you can see at this curve, the slope of this curve. Okay, I'm so sorry, this is a blunder of mine. Okay, okay, I can see in this is slope is higher at this part slope is higher, so just make it like this, same like the above curve. You can do it here like this. Okay, slope has to be higher in this part and lower at that part. So let's do it like this, or I will start from here. Let me try to make, okay, very fine curve. Okay, so this part is negative, this part is here positive. Now you can see here this point. Look, This is the most important feature which will ask millions of times in the exam. Look this point. What is happening here? At this point, this you can talk in between C and D. In CD span, bending moment has changed from positive value, this positive 10.88 value, to the negative 18.75, and the bending moment curve. What is this? This is a bending moment curve for CD part. CD span has crossed the initial line, this beam axis at this point. That is, bending moment is zero every at this point. So this point is called point of contraflexion, or you can call it as inflection point also. Okay, point of contraflexion, inflection. This is acting at x distance from C. So you have to find what is this distance. If you are in a little bit hurry in the examination, you can just do up to here, it's very much fine. But if you find this x distance, it will be most suitable. Okay, so for now I am going to find this x value. If you think the video has taken too long, you can skip this part, but this will be very much essential if you find the x value, because for frame analysis also you have to do in the similar way. Now to find this x distance, now what you have to do is, the x distance is coming in between the portion C to D. So this is a little bit complicated here. Okay, this is going to be very complicated. So let me first, what I have to do is, let me pause it. Okay, so let's see here. Let me change the color. Let's me one more for the final time. Let me change the color to this sky blue. Okay, this the orange is fine now. Let's see here. Okay, so I have to find the x value. What I have to find, this x value equals to what? Okay, so for that, I have to draw a section, because this bending moment was zero in between C point and this D point. So let me cut a section over here somewhere between C and D. You can make it anywhere like this. Okay, okay, this is a section. I call it section 1, section 1 II. This is at a distance of x meter from C. Okay, so this section has made a triangle of itself. Look at here, this triangle. But I don't know this value. I have to first find this h value, like we did earlier. This h value, I don't know how much is this. This h, again from the similar triangle principle, h divided by this whole is 5, must be equals to x divided by 6. So my h will be 5x by 6. So this orange triangle, this triangle orange part, will give me a point load of, okay, this is my point load of 1 by 2 into base is x, not 3. Okay, this is x into 5x by 6. And how much is this distance from this section line? This will always be equal to x divided by 3, that is x divided by 3. Okay, now I have to find the bending moment at this point. Look here. Okay, I have to find the bending moment at this big circle. Okay, this point, bending moment at this distance. So let me see mx value, how much it will come. Mx, so you can imagine I'm over here, I'm here, and I'm looking towards the left. Okay, so I am there and I will be looking towards the left from, okay, from here. So let me find the moment equation. This will give me a moment. Look at here, this force is going to give me a moment, and the value will be this value multiplied by this small distance. And you know the sign convention, this is okay. I am looking left from this section, from this point, so I have to follow this curve. So as for this will be negative, minus 1 by 2 x into 5x by 6, distance is x by 3. Very good. Now this 10 kilonewton, I have to see, I am at this point. Okay, I am at this point and I have to see left of this whole region, I have to see this point also, all up to the point A, okay? I have to see up to the point A. Now for that, this is 10 kilonewton meter couple, so this is only 10, this is only positive 10, okay? Okay, let me first adopt this all this. Okay, let's leave it for now. This 20 is also giving more movement, but it's negative again. Minus 20 into how much is the distance from this 20 all the way to this section? This is 2 plus x. Okay, so this is 2 plus x, and now this is 10.72 left. This is positive 10.72 plus distance is from A point to this section point. How much the distance is? 2 plus 2 plus this x, not 3. You don't get confused with 3. 4 plus x. Now this is my bending equation. As you can see here, x is multiplied 3 times here. So the power will be here x cube. That's why the curve we used was cubic parabola or just a cubic curve. Okay, so I got the mx equation like this. Okay, so my mx equation here, so I got mx equation here as, if I have to write it down over here, my mx equation is minus 1 by 2 into x into 5x by 6 into x by 3 plus 10 minus 20 times 2 plus x plus 10.72 4 plus x. Now this is bending moment equation. What is this? This is bending moment equation for which part? C to D span. Okay, so now I have to find this point of contact flexure. What was point of contact flexure? The point at which the bending moment is 0. So to find the bending moment 0 point, for 0 bending moment, just don't do anything. You just do mx is equals to 0. That is, you put all of this right hand part over here equals to 0 and equate for here. You will find x, a certain value for x. Okay, so let me do it and tell you the value. Actually it is a cubic curve, so there will be 3 values. Okay, let me first find out and then I'll tell you. So upon careful calculation, I have got the 3 values. One was coming 1.35 meter. Okay, the other is minus 0.67 and other is also minus 0. Just neglect these negative values. What I have got 1.35 meter from C. So this distance is 1.35 meter. So our point of contact flexure is now acting at a distance of 1.35 meter from C. That this point. Okay, so we have done this. Okay, this is, we have done the bending moment diagram. We have plotted the shear force diagram, and we have found the contact flexure point. So this is the complete solution for this beam. If you have been preparing for bachelor's level examination in as per the syllabus of Purvanchal University, you will be asked this question 8 marks, okay, for the finals. So this much you have to do it. So thank you all.